It's a question from the Matlab section. We have 5 minutes and we can do it right now. So it's a question 92. Yeah. It's a question 92. It says this. It says, by using the product like so, show that pi on 4 is equal to the expression like this lengthy expression, 4 times inverse cotangent of 5, take inverse cotangent of 239. And actually it also says verify this with with Matlab directly. Verify this with the Matlab directly. I'm going to do it right now. Here's a Matlab. So if I'd like to verify this directly, this one, I just compute this expression in the Matlab with a sufficient level of accuracy. Here's a computation. So I guess if I do like this, pi on 4, well, it's not enough accuracy. That's the thing which I learned yesterday. If you want to extend the number of digits, Matlab shows you in his responses. You do this format long command, and now you see it gives you more digits when you compute pi on 4. Now that's the left hand side of my expression. If I compute the right hand side of my expression, it will be 4 times inverse cotangent function. It has the abbreviation acot. In Matlab, you can easily Google that. If you just Google inverse cot in Matlab, you will come up with this answer. It's not like I remember this. I just learned it yesterday. So inverse cot of 5, take inverse cot of 239. That's the one. Well, it's exactly the same number up to the last decimal digit available. So in terms of the Matlab, these two numbers are identical. Even though it's not mathematical, I mean, this cannot be taken as a mathematical identification because we still have some error. There is still error present in both computations of the first number and the second number. Now, we're going to use Maple a little bit longer. Now, I'm going to show now that why this is true actually exactly in mathematical terms, and for that I'm going to use Maple as well, because I'm going to use Maple to expand this expression here. This expression, look at this. If I expand the binomial, here's the expansion for the binomial, 5 plus I to the power 4. Let's just do the whole thing together. 239, take I, bracket, bracket. Here's the complete expansion. Yes, it is. If you look close at this number, we see that the real part and the imaginary part are identical, and they exactly identical. So if you do this complete expansion, I have it here on my slide somewhere. Here it is. If you do this complete expansion, that's the expression you're having. These dots, they're hiding actually I computed this with the Matlab as well. Well, I didn't use Matlab yesterday when I was building the slide. I used some other computer algebra system, but it doesn't matter. So look, compare these numbers. We have 1, 1, 42, 44, 1, 1, 42, 44, and 0 the rest. So it's a sharp computation. The complete expansion gives you the number like this. You can now convert this number to the exponential form. Here's my conversion. Again, it's a sharp conversion. And that's the computation for the expression like this. Now, on the other hand, I can convert to the exponential forms the factors individually, this factor and this factor. Here's the conversion. Here, inside the brackets, that is the exponential form for the 5, take I. Here's the argument, cot inverse of 5, that's the argument of this number. When you raise this number to the power 4, it's very easily done in exponential forms. Here's the result of this. I raise to the power 4 the modulus, and I multiply the argument by this number. Similar job, if I do a similar job for second factor here, here's the modulus. And here's the argument. Well, this modulus, again, we can use Matlab for computing that. On the other hand, well, if you use Matlab for that, let's just try. Let's just see what Matlab gives you. I think that's the SQRT, it's a square root. Oops. Yeah, it's a square root. So if I go square root of 1 plus 239 square, well, it's not really a friendly expression. Yesterday, when I computed the same thing with the other computer algebra system, because you see Matlab, it's more focused on the numerical computations, where I used, for instance, Maple, it's more focused on symbolic computations. When I did this symbolically, the result actually was looking a bit better. It was root 2 there, rather than the horrible expression just Matlab spit out for me. But it's irrelevant, in fact, because all we need from this expression is the argument. So here we go. If I multiply now, we're almost done. If I multiply now, we know how to multiply two numbers in exponential forms. We multiply the moduli, is the product of the moduli, and here is a combination of the arguments. So now we have a temptation to identify this argument with this argument, but there is a catch, isn't it? When we have two exponential forms equal to each other, when we identify the arguments, before we can do that, we have to make sure that the arguments are within the same 2 pi region, 2 pi interval, because otherwise they may be different by 2 pi or multiple of 2 pi. So without this verification that the arguments, both of them within the same 2 pi interval, you cannot identify the arguments with each other. This one obviously between negative pi and pi. I'm going to convince you that this one is also between negative pi and pi. Here's my argument for that. I'll make the abbreviations. If I call alpha cot inverse cot of 5 and beta inverse cot of 239, from the properties of the cot function, we know that both of these angles, they will be between 0, and because 1 is less than 5 and 1 is less than this, cot is the decreasing function, so alpha beta will be less than cot of inverse cot of 1, which is pi and 4. And that is enough to conclude that this combination, on one hand, it's larger than negative pi and 4. I'm taking the smallest value here and the largest value here. The smallest value here is 0. The largest value here is pi and 4. That's why it's negative pi and 4. If I take the largest value here and the smallest value here, so it will be 4. It will be pi and 4 here, so pi together, and 0 here. It will be pi. That's why this combination also between negative pi and pi, and that's why I can equate this bracket to this pi and 4. Consequently, pi and 4 equal 4 alpha take beta. Remember this, you cannot identify the arguments unless you showed beforehand that the arguments within the same 2 pi interval. But from the Matlab point of view, we just verify that with two commands.